Hello everyone, welcome to MindMatrix. So here we are with the fourth lecture on operating system. So let's start the video. Before starting, let me introduce myself. My name is Anshul Sharma. I'm upcoming software engineer at Juniper Networks. Currently, I'm pursuing M.Tech in computer science from IIT Kanpur. I have more than 2 years of teaching experience. I have mentored more than 1,000 students and I have expertise in computer science and data science subjects. I secured All India rank 294 in GATE Computer Science, cleared ISRO NIC NAILET exam, also got selected as Administrative Officer at AIC. So this is our doubt discussion Telegram group that you can join. So you can scan this QR code and you will be able to join our doubt discussion group. Okay. And guys, before starting this video, uh, I would uh, I would request to all of you to like this session, share with your friends, those who are preparing for GATE 2024 and GATE 2025, and do subscribe to our channel MindMatrix. So let's start. So in the previous lecture, we have discussed how schedulers work, long-term scheduler, short-term scheduler, medium-term scheduler, what are the process states, right? We discussed the entire process state diagram. Now we are going to see how the CPU scheduling happens, right? So before, discussing further the algorithms of CPU scheduling, we are going to talk about various times related to the process. So let's see the first one, arrival time. Now what is arrival time? When the process enters in the ready queue. So in the last lecture we talked about process state diagram. So there we have new state, ready state, run, terminate, wait or block. So many states are there, right? So when your process enters into the ready queue, then this arrival time starts. Okay, so whenever your long-term scheduler is going to shift the process from the new state to the ready state, then the arrival time starts. So this is the arrival time. What is waiting time? Time spent by the process waiting in the ready queue for getting CPU. So as you know, in the ready state, processes wait to get the CPU, right? So that they can execute. So if they are waiting in the ready queue, in that case, that will be your waiting time. So waiting time is also equal to turnaround time minus burst time. Now, what is turnaround time and what is burst time? We will be discussing it further. Okay, so just wait for it. I will be coming back to the slide again. Then we have a response time. What is response time? Time after which a process gets the CPU for the first time after entering in the ready queue. So when your process arrives in the ready queue, right? And when the process gets the CPU for the first time, the difference of those two is your response time. So response time is time at which the process first time gets the CPU minus the arrival time of the process. Okay. You will be getting much more clarity when we are going to solve the questions based on this. What is burst time? So burst time is also known as a CPU time or running time. So here the burst time is time required by a process for executing on CPU. It is also called running time. It can only be known after the process has been executed. Let's say a process P1 is having burst time of 2 millisecond or 2 units, let's say. So for 2 units of time, the process P1 is going to get the CPU. Okay, so that is your burst time, also called as running time. Now, what is completion time? Time at which a process completes its execution on the CPU and takes exit from the system. So when your process completes its execution entirely and when it is going to terminate, that means going to exit from the system, that is the completion time. What is turnaround time? So turnaround time is total time spent by a process in the system. Total time spent by a process in the system. So now carefully observe this. A process, either it is going to execute, right? That means either it is going to get the CPU and it will be executing, or it is going to wait. These are the two possibilities, right? Either it is going to wait or either it is going to wait or it is going to execute. So turnaround time is nothing but the some addition of burst time and your waiting time of the process. Okay, so turnaround time is your duration. Turnaround time is your duration. Okay. Or we can also say turnaround time is nothing but completion time minus arrival time, because in between these two, either your process will be executing or your process will be waiting. Clear? So we can also understand in this way. Let's say we have one process P1, and let's say this is the timeline of process P1. Let's say for 1 unit of time, process P1 is executing. Okay, for 1 unit of time, process P1 is executing. So let's say this is the burst time. Now for another 1 unit of time, your process is waiting. Okay, then let's say for the remaining time, your process is executing. So what is going to be the completion time? Completion time is going to be the arrival time of the process when it arrives in the ready queue, and the completion time of the process. And this duration, this entire duration is going to be your turnaround time. That means the burst time plus the waiting time. Or we can also say turnaround time is nothing but the completion time minus arrival time. I hope it is clear now. Clear? So here we were discussing about the waiting time. So as we know that turnaround time is your burst time plus waiting time, or we can also say turnaround time is completion time minus arrival time. So waiting time is nothing but, from this equation we can get, right? Waiting time is nothing but your turnaround time minus burst time. Clear? So this is going to be the equation. Now let's talk about the objectives of process scheduling algorithm. What are the main objectives, right? That we need to, that we need to fulfill, that we want to fulfill when we are scheduling the processes. So first thing is we want maximum CPU utilization. We want our CPU to, for most of the time, it should be busy in executing the processes. We want that. So we want maximum CPU utilization. Second, we want fair allocation of CPU. The CPU should be allocated in a unbiased manner, right? That means fair allocation will be there. It should be allocated to each and every process after a certain time. It should not be like this, like one process is, keeps on executing and other processes, facing starvation. So we also want fair allocation of CPU. Third one is maximum throughput. We want maximum throughput. Now what is throughput? Number of processes that complete their execution per time unit. Okay, the number of processes that complete their execution per time unit is your throughput, and we want maximum throughput. That means we want maximum number of processes complete their execution per time unit, per unit time, I can say. The fourth one is your minimum turnaround time. We want minimum turnaround time. Now, why we want minimum turnaround time? We know turnaround time is nothing but your completion time minus arrival time. Now, if I want minimum turnaround time, that means the time at which the process arrives in the ready queue and the time at which the process completes execution, we want that duration to be reduced, to be minimized as much as possible. I hope it is clear to you. Now what else we want? We want minimum waiting time also. Why we want minimum waiting time? Because we want our process to keep on executing properly, right? We don't want our process to wait for certain duration. So we want to minimize it. We want that our process should be, should be getting the CPU properly, and it should be able to further execute and complete its execution entirely. So we want to minimize the waiting time. We don't want our process to wait for a longer time. Sixth, minimum response time. What is a response time? A response time is nothing but first time CPU allocation minus arrival time. This is our response time, right? Now, why we want minimum response time? We want minimum response time because if the process is, let's say, arriving at 0 units of time and it is getting the CPU, let's say, at 10 units of time, in that case the response time of the process will be much more, right? We want that if a process arrives in the ready queue, just after certain units of time or just waiting for some time, it should get the CPU so that it can start its execution. So we want minimum response time as well. So these are the main objectives of scheduling algorithms when we are scheduling the processes. Clear? I hope it is clear to all of you. Let's proceed further. So there are different CPU scheduling algorithms. Okay, so we have first come first serve, we have shortest job first, longest job first, we have shortest remaining time first, longest remaining time first, round robin scheduling, priority based scheduling, highest response ratio next scheduling, multi-level queue scheduling, multi-level feedback queue scheduling. These are the different CPU scheduling algorithms that we have. Okay, so we will be talking about it one by one and with examples also. So let's start. So in this video, I will be covering FCFS, that is first come first serve. I will be talking about shortest job first, and I will be talking about SRTF, that is shortest remaining time first. So for these three algorithms I will be discussing in this video, and other algorithms I will be discussing in the later videos. Okay, so let's understand what is preemptive scheduling and what is non-preemptive scheduling. So preemptive scheduling, as I discussed in the previous lectures also, I explained you what is preemption, right? When we are executing, let's say, P1 process, and we want to execute another process, so we are going to take back the CPU from the P1 process. We are going to do context switching, and then we are going to give the CPU to the P2 process, and it is going to execute. So that is preemption. Okay, that is preemption. So what is preemptive scheduling? It is used when a process switches from a running state to ready state. Remember the process state diagram that we discussed in the last video. From running state to ready state, preemption happens. So it is used then. Or from waiting state to ready state. From waiting state to ready state, if it is moving, then also preemptive scheduling occurs. Resources are allocated to the process for the limited amount of time and then is taken away, and the process is again placed back in the ready queue if it has the burst time remaining. So understand this, understand the meaning of this line, that let's say a process P1 is executing. Okay, let's say its burst time is, or the CPU time or running time is, let's say 4 units of time. Okay, now let's say P1 is executing and it has executed for 2 units of time. So 2 units of burst time is still remaining, correct? Now we want to schedule P2 process, and P2 is also having a burst time of, let's say, 2 units of time. Okay, so now P2 will execute. So P2, let's say P2 executes completely, and now the CPU we are again going to allocate to the P1 process, and you can see the burst time of P1 process, the remaining burst time of P1 process is 2. That means again we are going to place it back in the ready queue, right? And then CPU will be allocated to P1, it is going to move to the running state, and then it is going to execute further, and it is going to complete its execution. Clear? So this is what we call as preemptive scheduling. Okay, the algorithms based on this is round robin, so that is preemptive. SRTF, shortest remaining time first, is a preemptive scheduling algorithm. Priority based also, and there are many more. So we will be discussing that in the upcoming videos. Okay, what is non-preemptive scheduling? That means there is no preemption. Once you allocate the CPU to a process, it will be completing its execution, and then you are going to give the CPU to another process. So there is no preemption. Okay, there is no preemption. Clear? So it is used when a process terminates, that means completing its execution, or a process switches from running to waiting state. That means the process wants to perform some input output operation. Okay, if a process wants to perform some input output operation, we will be shifting, or the system will be shifting the process from running to waiting state, right? So in that case, we use this basically this non-preemptive scheduling is there. Once the resources are allocated to a process holds the CPU till it gets terminated, or it reaches a waiting state. So once you assign the resources, once you allocate the CPU to a process, so the process is going to hold the CPU till it terminates or till it reaches a waiting state. If it is going to reach the waiting state, then it is going to give the CPU back, okay, so that other process can execute. But if it is in the running state, it is going to terminate entirely, and then it is going to release the CPU so that that can be allocated to another process. Clear? So that is non-preemptive scheduling, no preemption here. The algorithms based on this scheduling is your SJF, shortest job first, right? We have priority based also. So in priority, we have both non-preemptive and preemptive scheduling. And FCFS, first come first serve, is also your non-preemptive scheduling algorithm. Okay, no preemption is there, and there are many more. So we will be talking about that, in the upcoming videos. Let's talk about our first CPU scheduling algorithm, that is first come, first serve. As the name suggests, the process which arrives first, we are going to allocate the CPU to that process first. Clear? So processes arriving first in the ready queue is firstly assigned the CPU. And in case of a tie, process with smaller process ID is executed first. Let's say two processes arrived at the same time. In that case, the process which is having the smaller process ID, we are going to execute that first. And it is always non-preemptive in nature. It is a non-preemptive CPU scheduling algorithm. Okay. What are the advantages and disadvantages of first come first serve? So if we talk about the advantage, it is simple and easy. Whichever process arrives first, just allocate the CPU to that process. So it is very simple to implement and easy. We can maintain a queue data structure, right? And it does not lead to starvation. Now this is very important point. Why? Because in GATE 2023 computer science exam, they asked a question, and the question was, which algorithm may lead to starvation. So there were four options given, and FCFS was also there in the option. So here, if there is one exception you can consider, that if a process keeps on executing infinitely, then other process may starve. What is starvation? Starvation is nothing but your indefinite waiting. That means other process are keep on waiting for to get the CPU. Indefinite waiting, right? So there is one exception is in FCFS, and there were options like A, B, C, D for in that question. I will be taking that question in the upcoming lecture. So CD was correct. There were some options given. I will be taking that question further, but in that question, gate authority approves both the answers. That means including FCFS and not including FCFS. So not including FCFS is quite logical, but there is one exception: when a process keeps on executing infinitely, then in that case other process may face starvation. So in that case, so they consider that case as well, and they in the answer key they release that both the answers are correct. So don't worry about it. I will be taking that question separately. So what about the disadvantage of FCFS? It doesn't consider priority or burst time of a process. So there is no priority concept here in case of FCFS. There is no a burst time, it doesn't consider burst time. Basically, on the basis of arrival time, it is going to decide which process will be allocated the CPU first, just on the basis of arrival time. Clear? There is one effect, that is convoy effect, that we see in FCFS. And what is that? Now let me explain you. Let's say a process P1 is there, process P2 and process P3. Let's say three processes are there. The P1 process is having a burst time. Let's say P1 arrives first, then P2, and then P3. Okay. P1 process is having a burst time or the running time, let's say 100 units. and P2 is having a burst time of 1 unit. Let's say P3 is having a burst time of 2 units. Now in this case, as P1 arrived first, so we are going to allocate the CPU to P1 first. Now as you can see, P1, the burst time of P1 is very high as compared to the burst time of P2 and P3. So due to this, the shorter jobs, right, the processes or the jobs which are having smaller burst time, they have to wait till the completion of P1 process, right? It is going to execute for 100 units of time, and then P2 will get the chance to execute, and then P3 will get the chance to execute. So this is we call as convoy effect, right? Convoy effect. So processes with higher burst time arrived before the processes with smaller burst time. Then smaller processes have to wait for a long time for longer processes to release the CPU, as I explained you through the example. Clear? So this is convoy effect which we observe in case of FCFS, first come first serve scheduling algorithm. Now let's solve one question based on FCFS. So here we have the process IDs. We have 5 processes, P1, P2, P3, P4 and P5. We have the arrival time, burst time, completion time we need to find out. We need to find out turnaround time, waiting time and response time, right? So arrival time and burst time is given to us here. Okay. Now we need to schedule the processes using FCFS. Using FCFS, we need to schedule these processes. Now, as we know, FCFS is based on the arrival time, the process which arrives first. We are going to schedule that process first, right? So there is one Gantt chart that we use to schedule the algorithms. So let's do it now. Now carefully see which process arrived first. So you need to see the arrival time column. So here you will find out that P3 is the process that arrived first, because the arrival time of P3 is 0, and for other processes it is more than 0. So P3 arrived first. Based on FCFS, we are going to schedule P3 process first. So at 0 units of time, P3 arrived. And what is the burst time? It is non-preemptive scheduling. So we are going to completely execute the process. Burst time is 2. So for 2 units of time, we are going to schedule P3 process. So let's make it 0 now. P3 has completed its execution. Clear? Now at 2 units of time, do we have any process in the ready queue? Let's see here. P1 is having the arrival time of 3. So P2 is having arrival time of 5, P4 is having arrival time of 5, P5 is having arrival time of 4. That means at 2 units of time, there is no process present in the ready queue. So let's say for 1 unit of time, if we see here, P1 is arriving at 3 units of time. So we can say from 2 to 3, the CPU will remain idle. CPU will remain idle. It is not performing any useful task because none of the processes present in the ready queue at 2 units of time. So for 1 unit of time, CPU will remain idle. Now at 3 units of time, we can clearly see that P1 arrives in the ready queue. So we can schedule P1 process here. And the burst time of P1 is 4. So for entire 4 units of time, we are going to schedule P1 process. So 3 plus 4, it is going to be 7 here. P1 has also completed its execution. Clear? Now at 7 units of time, P2 has arrived, P4 has arrived, P5 has arrived. All the remaining 3 processes have arrived, if we talk about at 7 units of time. So all P2, P4, P5, all 3 processes are present in the ready queue. Now which process to schedule first? So if you compare the arrival time of these 3 processes, that is 5, 5 and 4, obviously P5 will be executing first. So we are going to execute P5, right? For 3 units of time, so we can make it 0. So 7 plus 3, 10. So P5 has also completed its execution. Clear? Now we have just P2 and P4 present in the ready queue for the execution. right? So both the processes are having same arrival time, that is 5. So if both the processes are having the same arrival time, in that case we are going to consider the process ID. The smaller the process ID, we are going to schedule that process first. So P2 and P4. P2 is having smaller process ID as the number suggests, right? So we are going to schedule P2 first for 3 units of time because the burst time of P2 is 3. So for entire 3 units of time, we are going to execute it. So it is going to be 10 plus 3, that is 13. P2 has also completed its execution. Now it's time for P4 because the P4 is the only remaining process that is present in the ready queue. We can schedule it now. So for 1 unit of time, so we can make it 0, and 13 plus 1, that is going to be 14. So all the processes have completed their execution. Now what is the completion time? CT means completion time. Okay, so completion time, let's see here for P1. For P1 the completion time is 7 because at 7 units of time P1 completes its execution. So we can write 7 here. What about P2? P2 completed its execution at 13 units of time. So we can write 13 here. For P3, it completed execution at 2 units of time. For P4, it is 14. For P5, it is 10. So this is the completion time. Now we need to find turnaround time. What is turnaround time? Turnaround time is nothing but completion time minus arrival time, right? Or burst time plus waiting time, but waiting time we don't know now. So we can first find out turnaround time using this equation, that is completion time minus arrival time. So completion time minus arrival time, 7 minus 3, it is going to be 4. 13 minus 5, it is going to be 8. 2 minus 0, it is going to be 2. 14 minus 5, it is going to be 9. And 10 minus 4, it is going to be 6. Clear? What about waiting time? So waiting time we can find out how, that is equal to turnaround time minus burst time, the second equation of turnaround time, right? Waiting time plus burst time. So after rearranging we can find out waiting time is equal to turnaround time minus burst time. So turnaround time minus burst time, so 4 minus initial burst time we have to consider. Okay, what was given in the beginning? 4 minus 4, it is 0. 8 minus 3, it is 5. 2 minus 2, it is 0. 9 minus 1, it is 8. 6 minus 3, it is 3. So this is the waiting time of all the processes. Clear? What about response time? We know response time is what? First time CPU allocation minus arrival time of that process. Now what about P1? P1 got the CPU at 3 units of time. So first time CPU allocation happened at 3 units of time for P1. So 3 minus the arrival time of P1. Arrival time of P1 is also 3. 3 minus 3, it is 0. That means as soon as P1 process arrived in the ready queue, it got the CPU. That is the meaning, right? Because it is 0 here. What about P2? P2 got the CPU allocation at 10 units of time, and but it arrived at 5 units of time. So 10 minus 5, it is going to be 5. This is the response time of P2 process. For P3, first time CPU allocation happened at 0 units of time. Arrival time is also 0, so it is going to be 0. For P4, it is 13. 13 at 13 units of time, P4 got the first time CPU allocation. 13 minus the arrival time, it is going to be 8. And for P5, it is 7. 7 minus 4, it is going to be 3. Now you can observe one thing here. In case of, you can also write it down, in case of non-preemptive, and it is always true, in case of non-preemptive CPU scheduling algorithms, waiting time will always be equal to response time. In case of non-preemptive CPU scheduling algorithms, waiting time will always be equal to response time. As you can see here, Waiting time is 05083 and here also it is 05083. Clear? And that is very intuitive also, right? Because there is no preemption. So if there is no preemption, the waiting time of the processes will be same as the response time, because as soon as they arrives in the ready queue, they are getting the CPU allocated. Okay, like after some time. So waiting time will be same as the response time. That means only for that duration of time the processes are waiting. Clear? So this is true for all the non-preemptive CPU scheduling algorithms. Clear? And in the gate exam, they may ask questions like find out the average turnaround time, find out the average waiting time or average response time, right? So you know how to calculate the average. Just sum them up, turnaround time, just sum all these up and divide it by the number of processes. Similarly, average waiting time will be sum of all divided by the number of processes, and same for the response time as well. Clear? So I hope it is clear how to solve questions based on first come first serve CPU scheduling algorithms, how to schedule the processes and how to find out the respective times, that is turnaround time, waiting time, response time, and average of all these. Clear? Now let's see one more example, or the kind of question they may ask to find out the efficiency of the algorithm, or this the way we are scheduling the processes. So we need to find out the efficiency. And it is also given that 1 unit of overhead is there in scheduling the processes. Whenever you schedule a new process, 1 unit of overhead is there. So this is given to us, and after scheduling the processes we are getting this Gantt chart, and here you can see before P1 gets scheduled there is 1 unit of overhead. Before P2 got scheduled, 1 unit of overhead. So before every process there is 1 unit of overhead, right? So we need to find the efficiency. So if you see, for entire 23 units of time, out of that for 6 units of time there was a kind of overhead, or we can say the CPU was not performing anything useful task, right? It was idle at that time. So for out of 23, for 6 units of time the CPU remain idle, but we need to find the efficiency. So definitely it is going to be 1 minus of it. And in terms of percentage, if you want to find out, so this is going to be the efficiency of the CPU, that is 73.91% in case of scheduling it using FCFS. Clear? So these type of questions can also be asked in the exam to find the efficiency. And inefficiency is nothing but 100 minus 73.91, or basically 6 by 23 into 100. That is going to give you the inefficiency. Now let's talk about the other CPU scheduling algorithm, that is SJF, shortest job first, and SRTF, shortest remaining time first. So in case of shortest job first, as the name suggests, shortest job first, that means the process which is having lowest burst time, we are going to schedule that first. We are going to allocate the CPU to that particular process. Clear? So SJF, shortest job first, CPU is assigned to the process having lowest burst time. And in case of a tie, it is broken by FCFS. If the burst time of two processes or more than two processes are same, in that case we are going to consider FCFS. That means based on the arrival time we are going to schedule those processes. Clear? Now if we talk about SJF, that is shortest job first, it is having both the modes, non-preemptive mode and preemptive mode. When it is non-preemptive mode, simply by seeing the burst time of the process, you need to find out the lowest burst time. The process which is having the lowest burst time, you are going to assign CPU to it. You are going to execute it first in case of non-preemptive mode. But in case of preemptive mode, it shortest job first becomes SRTF, shortest remaining time first. And we are going to solve question based on that as well. Shortest remaining time first. Clear? In case of preemptive, it becomes shortest remaining time first. So we will be solving questions based on both the algorithms to get more clarity. Okay, but before that, let's see the advantage of this shortest job first and SRTF. So SRTF is optimal and guarantees the minimum average waiting time, right? Because we are considering the lowest burst time and it is also preemptive in nature, so it guarantees the minimum average waiting time. Okay. Now, what about the disadvantage? It cannot be implemented practically. Why it cannot be implemented practically? Since burst time cannot be known in advance. Okay, burst time cannot be known in advance. So we don't know the CPU time or the burst time of a process before even executing it. Okay, we can predict it. There are some methods, to predict the burst time. We will see that in this video only. But you don't know how much time will it take to a process, completely execute it. Okay, so we don't know that in advance. That's why it is practically cannot be implemented. Clear? This is the disadvantage. It leads to starvation of processes with longer burst time. Yes, this is possible. Let's say, if you are having, you know the in case of SRTF, if we say, if the process is having lower burst time, will keep on executing, and other processes are also coming that is having the lowest burst time. So in that case, the processes which are having longer burst time will have to wait, so they may face starvation in that case. Okay, so priorities with large burst time have poor response time. Not priorities, basically processes with larger burst time, they have the poor response time in case of these CPU scheduling algorithm. So let's understand how to schedule the processes using first SJF, that is shortest job first. Shortest job first, and it is non-preemptive. When we talk about preemptive, then it becomes SRTF, shortest remaining time first. So these are the processes given. Arrival time is given to us, burst time is given to us. Burst time is given like in this question, that okay, this process will take, just to see how the processes are scheduled. But practically burst times are not there, given in the advance. We don't know that how much time will take for a process to execute. So let's schedule it now. So first of all, you need to see, at 0 units of time, do we have any process in the ready queue? First, we need to see that whether process is there in the ready queue or not. So P1 is arriving at 3 units of time, P2 at 1, P3 at 4, P4 at 0, P5 at 2. So at 0 units of time, only one process is there in the ready queue. So we have P4 process. We are going to schedule that. It is non-preemptive. So we are going to execute it completely for 6 units of time. The burst time of P4 is 6. So 0 plus 6 is 6. P4 has completed its execution. Done. Now at 6 units of time, do we have any process present in the ready queue? Yes, P1 is there because the arrival time is 3. P2 is there, P3 is there, and P5 is also there. So at 6 units of time, all the remaining processes are present in the ready queue. Now we need to see the burst time. The process with the lowest burst time we have to see first. So all the remaining processes present in the ready queue. Now compare the burst times of the remaining processes 1, 4, 2, 3. So clearly you can see P1 is having the lowest burst time. So we are going to schedule that first. So 6 for 1 unit of time we will be scheduling entirely. So 6 plus 1, it is going to be 7. P1 has completed its execution. Clear? Now P3, P2 and P5, these are the 3 remaining processes present in the ready queue. We will be checking the burst time. We will be comparing the burst time. P3 is having the lowest burst time, 4, 2, 3. So P3 is having the lowest burst time. We will be scheduling that first entirely. So 7 plus 2, it is going to be 9. So P3 has also completed its execution. Now P2 and P5 is remaining. If you compare the burst time, P5 is having smaller burst time. So I will be scheduling P5 first. So for 3 units of time, so 9 plus 3, it is going to be 12. P5 has also completed its execution. Clear? Now what about only the remaining process is P2. So we will be scheduling that now, P2. For 4 units of time, because the burst time of P2 is 4. So we can make it 0. 12 plus 4, it is going to be 16. P2 has also completed its execution. Clear? We can find out the completion time using this Gantt chart. So for P1, completion time is 7. For P2, completion time is 16. For P3, completion time is 9. For P4, completion time is 6. For P5, completion time is 12. What about turnaround time? Turnaround time is nothing but your completion time minus arrival time. So completion time 7 minus 3, that is going to be 4. 16 minus 1, that is 15. 9 minus 4, that is 5. 6 minus 0 is 6. 12 minus 2 is 10. What about a waiting time? Waiting time is nothing but your turnaround time minus burst time. Clear? So 4 minus 1, that is 3. 15 minus 4, that is 11. 5 minus 2, that is 3. 6 minus 6, that is 0. 10 minus 3, that is 7. So we can find the average turnaround time, we can find the average waiting time. And as I told you, in case of non-preemptive CPU scheduling algorithms, waiting time will always be equal to response time. So we don't have to calculate response time separately. It is going to be same. Clear? You can verify also later on. Clear? So in this way we schedule the processes using shortest job first. Now let's talk about SRTF. SRTF, shortest remaining time first, which is a preemptive CPU scheduling algorithm. And you have to see the execution carefully here. Okay, so let's make the Gantt chart here. Now, so first of all, at 0 units of time, which process arrived first in the ready queue? So you can see P4 arrived first. So P4 we are going to execute. But this SRTF is preemptive in nature. Preemptive scheduling. So we are not going to execute completely for 6 units of time. No, we are going to first check, okay, for one, let's say if I execute P4 for 1 unit of time, do we have another process present in the ready queue? So if I execute P4 for 1 unit of time, 6 will become 5. Now, at 1 unit of time, I have P4 plus I have P2 also. Let me write here P1, P2, P3, P4 and P5. So at 1 unit of time, P2 has also arrived in the ready queue. Now there are 2 processes present in the ready queue. Now we have to compare the burst time of the processes, and the lowest process which is having the lowest burst time, we are going to schedule that first. So here you can see P2, the burst time is 4. For P4, the burst time is 5. So P2 is having the lowest burst time as of now. So we are going to schedule that first. Okay. Again, for 1 unit of time, I will be executing it. So 1 plus 1, it is going to be 2. And here I can make it 3. Clear? Because at every unit of time, we have to check whether there are more processes present in the ready queue or not, whether there are more processes arrived in the ready queue or not. And then we need to compare the burst time of the processes present in the ready queue. The process which is having the lowest burst time, we are going to schedule that first. So again, at every unit of time, we have to check this. Okay. So at 2 units of time, now you can see P5 has also arrived. At 2 units of time, P5 has also arrived. So we have P5 now as well. Clear? Now again, we need to compare the burst time of these 3 processes, P4, P2, P5. P2 is having 3, P4 is having 5, P5 is having 3. So both P2 and P5 are having 3 units of burst time. So in case of a tie, always prefer what? Always prefer the arrival time. Or you can say, always prefer the arrival time, or basically you can say the process with smaller ID as well. So here if you see, The process with smaller ID, which one it is? P2. So we are going to schedule P2 first. So we are going to schedule P2 again because both are having the same burst time. So we are going to schedule P2 because P2 is having the smaller process ID. So for again 1 unit of time I will be executing is 2 plus 1, it is going to be 3. And we can make it 2. Clear? We can make it 2. Now, at 3 units of time, P1 has also arrived in the ready queue. At 3 units of time, P1 has also arrived in the ready queue. So P1 is also there. Now we need to compare the burst time of the processes. So you can clearly see P1 is having 1 unit of burst time. That is the lowest among all the processes, right? So I'm going to schedule P1 now. 3 plus 1, it is going to be 4. I can make it 0. P1 has completed its execution. P1 has completed its execution. Clear? Now, at 4 units of time, P3 has also arrived because the arrival time of P3 is 4. So I can write P3 here. Right? Now, among all the processes, you need to check which one is having the smaller burst time. P2 is having 2, P3 is also having 2, P4 5, P5 3. So you can clearly see that P2 can be scheduled first because it is having the lower process ID. So P2 can be scheduled. Let's say for 1 unit of time, let's say if I execute it, so 4 plus 1, it is going to be 5. I can make it 1. But if you see here, now among all the processes, P2 is having the smallest burst time and all the processes have arrived. Now there is no more process that is going to arrive further in the ready queue. So we can schedule P2 again as well. 5 plus 1, it is going to be 6. We can make it 0. P2 has completed its execution. Now we have P4, P3, P5. If you compare the burst time, P3 is having the smallest burst time. So clearly we can schedule it for entirely. We can schedule it entirely because we know no more processes are going to arrive now. As we can see, all the processes have arrived in the ready queue. So clearly we can schedule the P3 process for entire 2 units of time. 6 plus 2, it is going to be 8. So P3 has also completed its execution. Clear? Now if you compare the burst time of P4 and P5, P5 is having the smallest burst time. So now we can schedule P5 entirely because no more processes are going to arrive. So 8 plus 3, it is going to be 11. So P5 has also completed its execution. And then at the end we have P4. At the end we have P4. So 11 plus 5, it is going to be 16. All the processes have completed their execution. And this is the way these processes are going to be scheduled. Now let's find the completion time. So in case of preemptive CPU scheduling algorithm, always try to scan it from the right hand side. So you have to go from right to left so that you don't commit any mistake while writing the completion time of the process. Clear? So if you see the P1, if you see the completion time of P1, if you see, okay, here it is. So 4 is the completion time of P1. What about P2? Here it is. So 6 is the completion time of P2. What about P3? Here it is, 8. For P4, it is 16 completion time. For P5, it is 11 completion time. Turnaround time. Turnaround time is nothing but your completion time minus arrival time. So 4 minus 3, it is going to be 1. 6 minus 1, it is going to be 5. 8 minus 4, it is going to be 4. 16 minus 0, it is going to be 16. 11 minus 2, it is going to be 9. Waiting time is equal to your turnaround time minus burst time. So turnaround time minus burst time, 1 minus 1, it is going to be 0. 5 minus 4, 1. 4 minus 2 is 2. 16 minus 6 is going to be 10. 9 minus 3, it is going to be 6. So you can find the average turnaround time, average waiting time as well. And let's say if I add response time also. Let's say if I want to find the response time, just to show you how it is in case of preemptive. So the first time CPU for P1, for the first time CPU got allocated at 3 units of time for P1. And the arrival time is also 3. So 3 minus 3, it is 0. You know what is response time, right? First time CPU allocation minus arrival time. Clear? So response time is 0. For P2, for P2, yes, here it is. First time CPU got allocated for P2 at 1 unit of time, not at 2 units of time. So 1, and the arrival time, it is 0. Response time is 0. For P3, first time CPU got allocated at 6 units of time. Arrival time is 4. 6 minus 4, it is going to be 2. For P4, first time CPU allocation at 0 unit of time. Arrival time is also 0. 0 minus 0 is 0. For P5, it is 8. So 8 minus 2, it is going to be 6. So this is going to be the response time for all the processes. So you can see there is some difference. So in case of preemptive, response time may or may not be equal to waiting time. But in case of non-preemptive CPU scheduling algorithms, response time will always be equal to the waiting time. I hope it is clear how SRTF works, right? How we schedule the processes using SRTF algorithm. Now let's talk about the some important points. Practically, it cannot be implemented, but theoretically can be implemented. And min heap can be used where root element contains the least burst time. We know in case of min heap, the root element is going to have the smallest value, right? So we can use min heap. We can have the burst time in the min heap, right? In all the nodes, we can have the burst time values of the processes, and the process which is having the lowest burst time, it is going to present at the root level. So we can use min heap data structure to implement or to write the program for it. Okay, but as we know, burst time we don't know in advance, but in case how we are going to see it, we can, if we say okay, these are the burst time of the processes, then we can use the program, we can use this data structure. Time complexity for n processes. So adding element in min heap takes log n, deleting element from min heap again takes log n, and for n processes it is going to be n log n. This is going to be the time complexity. Now, as we don't know the burst time in advance, but we can predict, we have some techniques by which we can predict the burst time. So there are two techniques. One is a static technique and other one is your dynamic technique. In case of static technique, to predict the burst time of the processes, we have two types again, based on the process size or based on the process type. Okay. And in case of dynamic, we have simple averaging and exponential averaging. So let's see one by one. So techniques to predict burst time. So first we are going to talk about static. Okay. So we have one way of static prediction of burst time is process size. So in this case, what this technique does, let's say if you want to predict the burst time of P1 process, and that is of, let's say, 4 KB. P1 process size is 4 KB, and let's say you have some P5 process which you executed, and the size of process P5 was also close to 4 KB, and it took 4 units of time. So we also going to assign 4 units to P1 process. This is the static way of doing it. This technique predicts the burst time for a process based on its size. Burst time of the already executed process of similar size is taken as the burst time for the process to be executed. So as we see, P5 process is also a 4 KB, and as we saw that it took 4 units of time to complete its execution. So we are also going to predict that, okay, it is also going to take 4 units of time. This is very static, right? This cannot be true always. Predicted burst time may not always be right. This is because the burst time of a process also depends on what kind of a process it is. So for that, we have the second one, which is process type. This is also static technique. Clear? So in case of process type, it predicts the burst time for a process based on its type. So let's say if it is a OS process, operating system services process, then we are going to assign, let's say, 3 to 5 units of time. If it is a user based process, if it is interactive, then 5 to 8 units. If it is a foreground process, 10 to 15 units. If it is a background process, 15 to 20 units. So like this, we are going to predict the burst time in a static way. But static is not going to be correct or close to the what it should be, right? So then we talk about dynamic prediction of burst time. So for that, we first have a technique, simple averaging. Basically, we are going to take the average of all the processes. So let's see here, given n processes and burst time of each process pi is ti. So we know the burst time of already executed processes. We are going to find the average of the burst time. So we are going to sum up the burst time of all the executed processes, and we are going to divide it by the number of processes. So this is one way of predicting the burst time. This is simple averaging. Okay. The last method, that is also dynamic technique, that is exponential averaging. So in case of exponential averaging, what we are going to do here is, carefully see, t of n plus 1 represents the predicted burst time, or the process. Let's say n plus 1 is a process, I want to predict the burst time for it. So t of n plus 1, capital T of n plus 1, represents the prediction time of the next process. And here alpha is the smoothing factor. And its value varies from 0 to 1. Okay. Small t of n represents the actual burst time of process PM. That means actual burst time of a previously executed process. Because it has been executed completely, now we know what is the actual burst time of that process. Then we have 1 minus alpha, and then we have capital T of n. So this is predicted burst time, what we predicted for that previous process. Okay, so this is the formula for exponential averaging. And alpha we have just to maintain a balance between the prediction and the actual one. So this is exponential averaging. Let's see one example based on exponential averaging. So we have T1, T2, T3, T4. These are the actual burst time of 4 processes. Okay, the previously 4 processes that has been executed. This is the given actual burst time. And we need to find T5. That means we need to predict the burst time for P5 process. Okay. T1 is also given, that is the predicted burst time of P1 process is given to us, and the value of alpha is given, that is the smoothing factor. So first we are going to calculate T2 because we need to calculate T5. So first we have to start with T2, then T3, then T4, then T5. So we know the formula, that is T of n plus 1 is alpha Tn plus 1 minus alpha capital Tn. This is the formula. Clear? This is the formula. Right. Now we need to find Tn first. So alpha, that is 0.5 into small tn, that is previous actual burst time of previous process, which is T1. Before T2 it was T1. So into 4 plus 0.5, 1 minus alpha, that is 0.5 into 10. That is the predicted burst time of P1. So we got 7. Now we can use this value, T2 value, for predicting T3. So 0.5 into 8, that is the actual burst time, plus 1 minus alpha, 0.5 into 7, that is 7.5. Similarly, we can calculate T4, 0.5 into actual burst time of previous process, that is 6, plus 1 minus alpha, 0.5 into 7.5, predicted burst time of P3 process, 6.75. And similarly, we can find T5 as well. So this is what we have as the predicted burst time for P5 process. Clear? So this type of question can also be asked, and we have covered that in the detail in this lecture. That's it from this video. I will be covering other CPU scheduling algorithms in the upcoming videos. So stay tuned. You can also join our MindMatrix channel on WhatsApp. You can join our doubt discussion Telegram group. You can also scan this QR code to join this group, and you can ask your doubts there. Don't forget to subscribe, like, share, and subscribe to our MindMatrix YouTube channel. Okay. And if you have any doubt related to any question or any concept, you can ask in this group. I will be answering your doubts for sure. Okay. Subscribe to our YouTube channel. We are putting a lot of efforts to give you the best quality content for all the subjects of gate computer science and data science and AI. So one by one we will be covering it. So also share with your friends, those who are preparing for gate exam and those who are going to appear for it, so that everyone can get the best quality content that we are providing. Thank you everyone, stay tuned, we'll see you in the next lecture. Thank you, bye bye.